Hi, everyone, and welcome back to Programming for Posterity. I'm your host, as always, Nelson. And today we're going to be talking about the rendering. We're going to do a deep dive on rendering walls in my Raycaster game engine. Um, and before we get to that, we're also going to do a bit of a tour of the top level structure of the game engine. Um, and we're also going to do a bit of a tour of like what happens in the camera every frame when we're rendering out a frame, but then we're just going to zoom in only on walls. And this is the first episode, well, not the first episode. This is the second episode of the series, but it's the first episode that's going to be like drilling in onto a particular topic. The previous episode was more of like an introduction to the series and like an overview, like this overview here that I showed at the end of the previous episode. So the part specifically, can you see my highlight here? Yeah. The part specifically that we're going to be doing now is drawing walls, but also on the way there, we're going to do these kind of high level tours, like I said. Okay, so you can get right into it then. Um, hold on a sec, this is not lined up. There we go. That's right now. Sorry about that. So to just quickly recap what we're talking about here, this is what the game engine. Oh, hold on a sec. Forgotten my workflow here. Do I not have the game up here? This is annoying. Oh, okay, there it is. Hopefully I can edit that out. So this is what the game engine looks like at the moment, right? Yeah, there's a guy here. He'll get mad and throw some fireballs at us. Fireball? Out of practice. There we go. Oh, that's better. Cool. So that's what we're talking about when we say we're rendering, this game. And I will now start at the let's start at the very, very top. Let's start at the absolute top of the game, of the program, right? This is the very first thing when we start up. Well, yeah, it basically is the first thing, right? Pretty boring. What happens in game initialize? Oh yeah, this does tons of stuff actually. The most interesting stuff here is probably loading resources. So yeah, like load music, load sound effects, load textures. And then aside from that, lots of configuration setup. Like this is some setup for SDL stuff. Actually, there's more interesting SDL setup down here, isn't it? Yeah, initialize audio, detect if there's a game controller, create a window, all this kind of stuff. We won't go into detail on those right now. You can just look up SDL documentation, I guess. But it's not super interesting stuff. There's some stuff to do with like scaling the size of the window, maybe that's slightly interesting. There is this, which is interesting. So window logical width 640 pixels means that we're fixed to 640 pixels width in the let's say like the surface that we're going to render stuff to in SDL. And that's sort of important because as we'll get into later on, this is like a Raycaster engine. And so 640 width here is important because we're gonna actually send out 640 rays. We're gonna do 640 raycasts to find columns of pixels in the game world to draw. So we'll get to that later on. That's important, this number. Yeah, otherwise, sure, we can go back to here. And then run loop. Shutdown is not interesting. I mean, whatever. There could be no shutdown, right? Who cares? Whoopsie. Just broke it. There could be no shutdown, and who cares, right? Because the program's going to go away anyway. Operating system's going to rip it. But yeah, this is when you're playing the game, this is the thing that you're interacting with, right? So so yeah, while is running. So this is just a way to shut the game down, right? When we want to shut the game down, we can set this global flag is running, and this won't go anymore. It'll do the shutdown. So at this level, what's interesting? Well, update mode is a way to defer changes in the game mode. So we have we can change the game mode to player. Oh, sorry, so this is the pending game mode, right? So this is not what the game mode is now. This is like, are we changing it to something? And none means we're not changing it to anything, right? It's going to stay whatever it is. It's going to stay. If we're changing to player, so we have player, map editor, title menu, game over, and intermission. These probably self-explanatory. Player is when you're playing the game, like when you saw me playing it. Map editor is, oh, I still have the game open. I didn't even close it. I'll show you. Map editor is this, right? You can modify the map and do stuff. You can put down things. Right? You can delete things. You can draw different kinds of tiles. Actually, I wanted to undo. We can undo stuff too. Yeah, so that's what that is. Title menu is like the game menu. Actually, I can show you that too. Why not? So we'll go back there. And I will load into the level, and then this is not title menu, right? This is just like a main menu. This is the menu, pause menu, let's say, right? Okay. But if we do this, we'll exit out of the main menu. That's the main menu, right? So this is a different game mode. And game over. I think I probably showed that already. That's when you die, and it says, "Do you want to load another save, or do you want to quit?" I think. And intermission is when you finish a level and it's saying, "Congratulations, you finished the level," whatever. That's intermission screen. That's a very boring one at the moment. And then yeah, in this switch, we just basically each one we just call a different function. Is there anything else interesting here? Oh yeah, we stop the music in when if the game mode is actually changing, we stop the music just to allow the new one to start its own music or have no music, whatever it wants to do. And we also call this is a little bit of a hack maybe, but just to keep things consistent in the UI, we call this UI init context as well when the pending game mode is not none, like when we're changing game mode, so it has a chance to reinitialize everything. And then yeah, also at the end, so these don't, when we call these functions to actually do the transition, we don't set pending game mode to none, but after they're done, we set it to none. That's not super interesting. Okay. Process input, like, so in the previous video, I talked about this general game loop that kind of applies to most kind of games, or maybe all kind of games. On each frame, you'll do input, update, output, right? And that's actually happening here explicitly, right? Process input, it goes through and reads a bunch of input state. This is what is it? This is pumping pumping SDL for events to do with inputs, right? Anything interesting? I mean, yeah, quit is not very interesting. What is interesting? On mouse motion, we'll keep track of the relative mouse motion. Yeah, controller add removed, and then we can set up a controller if controller is added or removed. And what else? Oh yeah, this is pretty interesting. So this is to do with if we have like input enabled. This is so if you can type text into text fields in the game and it works because just looking for individual keystrokes to input text, like the way that you would for button presses, is not. It doesn't really work. That won't perform well. Anyway. Yeah, blah blah, lots of stuff to do with reading inputs. And then this is the interesting thing that I was looking for. Sorry for the detour there. But anyway, this is kind of the interesting thing, like probably is handle play input, right? So we've done a bunch of stuff, processing a bunch of input stuff. Now we go to handle play input, and handle play input does cool stuff. This is like, depending on how the mouse moved, we turn the player, right? Or look up or down. Or if the player clicked a button, then we set some state so that if the player is in a particular state and they click the button, then they shoot, right? Where is that? Where is the shoot one? Isn't that the most exciting example? Where is shoot? Let me shoot. I want shoot. Yeah, here we go. Yeah, so here we do shoot. Is shooting is equal to get input hold is shoot. And then, oh yeah, and this is just to do with like, maybe this is not a great way to do it. This is just to do with like, if they're using a gamepad, are they holding the trigger, right? As opposed to, because this is, we'll cover this in another episode maybe. This is my sort of input system for doing, having like a layer of indirection, being able to rebind keys and stuff. But this is for a button. So get input hold is for a button. The name doesn't make it clear, but it's for a button. So this axis, so trigger on a gamepad is an axis, so it can't be covered by that. We can't have a button binding for the axis, so we can check for that separately. That's why it's a separate thing. And then other stuff, like if they press the button to open the map, if they press pause, if they press weapon binding keys, if they holding the melee button, right? Or the grenade button. These might not exist in the finished game, but at the moment you can hold a button, particular button to do melee, particular button to throw a grenade. And then others, like there's some fairly complicated stuff to do with movement, forward, backward movement, strafing, mouse movement stuff to support control styles like in Wolfenstein 3D, where you could use the mouse to strafe left and right and the arrow keys to turn. And then if you hold the run button, then the mouse strafing strafes you further, I think, and is like very, very, this is kind of bending over backwards to support Wolfenstein 3D control stuff for some reason. Not for some reason. To help out particular people who were testing the game who wanted that, right? That's okay. Yeah, so there's lots of interesting stuff there. So that's mostly what the update, that gives you a flavor of what the update is like. And no, that's not what I wanted. I wanted, is it game update? I think so. Whatever. Let's just do what we did the first time. Run loop. There we go. Oh yeah, okay. So yeah, game update is the next thing that we wanted, but we'll come back here. So now we've looked at update mode. We've looked at process input. Now we're going to look at game update. Game update. We come in here. Let's see. Yeah, we like sort of calculate some stuff like how much real time has passed, or how much not real time. How do I describe that? Not real time is like when simulation is running. Real time is like on the clock, right? So that's all pretty boring. But then this is interesting, right? This is really interesting stuff in the game, I think, anyway. This is like a whole, there's like a few different separate worlds of stuff going on in the game, right? In the input world, there's like these different things like checking stuff through SDL or even through the operating system or drivers or whatever to do with inputs. And then there's, so that's kind of one world. And then there's like uh, using that information to decide what the player was trying to do on the previous frame. That's another world. And then now in that's another thing. And then now in the update world, we've got all these things, right, which are like completely different stuff. So update physics, we go in here, we just like treat all of the actors in the world as though they're just these inert objects, basically, that have some properties on them. We just chug through and update their positions and do collisions between them and stuff. Update active sequences, we go through the same set of actors in the world, but now we're not treating them as physics objects. Now we're treating them as sort of state machines. And we take a look at, for each one, we take a look at what is the state that it's in now. A lot of them are just going to be in some dead state because they're a pickup or they're a tree or something, right? So they're in some dead state, it's nothing to do. But then other ones like, or yeah, I mean, there could be a tree or a pickup that's animated, and then it's not in a sort of a dead state. But say it's a monster. We're going to look at the state that it's in. We're going to see, is there any time left on the state? And if it has some function that runs every frame, then we're going to call that function. That function might decide there's some important thing has happened and it wants to transition to a different state, and it's going to do that, etc. So that all happens here. You can see we go through, and then for one particular actor, we will get, let's see, yeah, we'll get the sequence that they're in, and then we'll see this, let's see, duration is less than 0. Then go on to the next one. Yeah, so this is I think saying so duration less than 0 is a little trick. We use just like a sentinel value. If the duration is negative, then that means that we never transition out of this state. We're just stuck in this state, right? That's like a dead end kind of state, like I was saying. So we don't waste any time on it. But otherwise, we will, let's see. Yeah, there's some nuances here to the order that we update stuff to avoid miscounting time elapsed when we transition between states. So that's a little bit weird. And actually, I guess we'll go through this in depth in another thing. When we talk about animations, when we talk about actors, we'll go in this in depth. But just suffice to say, right, what's happening here is that for each actor, we're figuring out if we need to change state, and then if we do, then to change state. And also to call the, we will also be calling the function on these guys based on what state they're in. That's what updating them means, right? Update player hands is exactly the same thing because the player hands are an actor, but it's just that same thing, but done just only for one. See, there's no loop here. We don't do it for any other actors. We just do it for this actor. Easy. And then update dynamic tiles. This is a really interesting thing. This is like a whole video or several videos on its own. This is how all the stuff in the game, like moving floors and ceilings, like they move over time, or, you know, as a result of like a trigger, say, or how doors open and close, how push walls move. Is there other stuff at the moment? I don't know. That's some examples though, right? So this is, again, it's updating similar kind of way to like the actors thing. It'll go through all the dynamic tiles that we have, and it will do this update for each one of them. Yeah, here you go. Here's the different types, right? And these all behave differently when they get updated. And height move, they can be kind of different. It could be a floor that's moving or a ceiling that's moving, or both of them could be moving. They could be moving in different directions. And yeah, they can be in all different states. There's quite a lot of stuff in here. It's pretty complicated to just go into here, but we'll on a future video we'll go in depth and explain how that system works. So that's all the different kind of stuff that changes, right? Like the stuff that's dynamic in the game is like there's physics objects and actors, which are the same thing. They're the same kind of object, but they're behaving in two different ways, and we update them in batches in different ways, right? And player hands is it's sort of basically just an actor, but it's when you're playing the game, you know, and you see your gun and you're shooting your gun or whatever, you're swapping guns, stuff like that. That's the player hands, right? That's how they do that. And that has animations, obviously. And the dynamic tiles is geometry. Yeah, I think that's fair to say. It's geometry that's dynamic in some way. So a door that opens and closes, a push wall, ceilings and floors. Okay, so now that's the entire game at a high level explained, right? We got this run loop. So you can believe me. Sorry, actually, that's true. Generate output. So that's all of the kind of like stuff about the internal state of the game. But then this is the renderer now, right? So game generate output. So a few things we do here. We set some background render color. We do some stuff with SDL, get like a surface to render to. I don't know if this is. I think this is necessary. We're just making sure that the music volume is set right. And then depending on, so we covered this before, the game modes, right? So if we're in map editor mode, we call this do map editor GUI to draw the map editor GUI that you saw before when I was showing you the map editor. If we're in player, then we draw camera, and then the rest of this is not that interesting, I'm going to argue. So draw camera is like drawing everything that you see as the player. These other things are like if the pause menu is open, draw the pause menu. If the map's open, draw the map. If we're saying show perf display, which I think we always have on at the moment, but that's like a developer thing. When you're a player, you wouldn't have that turned on. You show that. I think also, player HUD is in here. So that's kind of interesting, but you know, obviously it's less interesting than drawing the camera. It's just drawing maybe some flat textures and some text and stuff like that. Okay, and there's a timer wrapped around this that we use to keep track of how long it took us to draw the UI. Then if we're in the title menu mode, all we do is draw a title menu. This draw melt is interesting. And actually it's in every one of these modes, isn't it? Oh, except for map editor. So this is interesting to talk about. Maybe we'll do a video on that specifically because I think it's cool. Anyway, so title menu, we draw the title menu. Game over, we draw the game over. Intermission, we draw the intermission. These ones are really straightforward, right? That's good. Draw melt. Actually, there's probably not even any point in looking in here because this is just gonna look so weird. So don't worry about that. But I'll show you what it looks like in the game, right? So do I have the game open? Yes. Okay. So if I go in here and I do let's say new game, you'll see, see that effect? It does, the screen melts down, right? That's what draw melt is doing. Yeah, that's what draw melt does. Calling this function on a frame will go in and check how much, how long have we been melting the screen for, and it also will have saved the whole frame buffer from before we started doing the melt, and then each frame it will check how long is left, and then it will kind of like push pixels down in that frame buffer to draw a particular thing so that it does that effect. And then when we've finished melting it, calling this doesn't do anything, I think. Is that true? Yeah, so if there's no more time left on this is just a no-op. Okay. And then now I think we can say that generate output. Yeah, so now we can say we've covered all of this stuff. So we've gone over the entire, for a frame, this is what we do every frame. And this stuff here is not interesting. We copy the keyboard state from the current frame into the last frame. That's the last thing we do, so that next frame will have access to the last frame's keyboard buffer and this frame's keyboard buffer. We could probably do this in a different place or whatever. We could make it nicer. The reason I do it at the very end, I think, is What do I do at the very end? Actually, you know what? It doesn't matter. I'm not going to do that. But the reason we do that is so we have access to the last frame's keyboard level. Okay, that's fine. Okay, so let me just refer back to my notes here. Yeah, so we've finished a tour of the top level game and engine, right? I'm going to say now we're going to zoom in on this guy here, generate output. And we'll zoom in on what's interesting for this video is draw camera, right? This guy here. So draw camera is cool. This function, this file is pretty big, as you can see from the line numbers there. Now, firstly, before I go into it, actually, I have this here. Yeah. So before I go into it, I'll just like get some terminology out there to kind of mull over while we're going over this. So this game is software rendered, right? We're rendering all of the camera, the game camera. Let's say for the sake of argument, we're rendering the entire game like in the CPU, not in the GPU, right? So every pixel that's going to get shown for the game on the screen, we're deciding what color the pixel is, or the final color of the pixel in the CPU, not in the GPU. Modern software rendering, right? I would say set up a bunch of state. I mean, Vulkan, they don't like to say set up a bunch of state, but whatever. You set up like a whole bunch of stuff about a frame in terms of, like vertices and geometry based on the vertices, like in lists of indexes and all these like configurations, how things should be interpreted and what things should happen at different points in the pipeline and blah, 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 blah. And then you just kind of like call some function and magically everything happens, the pipeline runs, and you end up with all the pixels on the screen. And you didn't say in your program, or at least in the program that's running on the CPU, you never actually said what color should go on any pixel, right? But here we're really saying for each pixel, like this is the color it should be. And what I'm going to refer to as the thing where I say what the colors are is a frame buffer. It's not really true, right? Because ultimately what's going to happen is it's going to get sent to a GPU, probably. And we're going to be using some kind of API like that. And so through SDL2, what we do is, and I promise this is relevant because we're talking about it being software render, right? So just to explain and get it out of the way, we have, let's see, yeah, this camera out texture, right? This camera out texture is what we're going to write. We're going to write all the pixels to. And then at the very end, what we're going to do is, unlock the out texture. And then we're going to create a quad that covers the entire screen, or the entire window. And we're going to render a copy of the camera out texture to the entire window, right? So the entire window gets covered up by this. So this part here that I've got highlighted, this is doing stuff in the GPU, right? It's got a quad that covers the entire window and it's going to draw a texture to it. It's a pretty boring thing to do in the GPU, right? But it does, I guess, end up result in some shader running to texture a quad, right? So that's really GPU stuff, or at least most of the time it would be on most people's computer, unless somehow you have your computer set up to actually do software rendering, in which case I guess it ends up redoing everything we did in the operating system or something, whatever. Okay, so that's out of the way. I just wanted to be really specific about what's happening. This is doing software rendering, and as I said, it's a Raycaster, right? But this is the tour of the what did I call it? I said tour of the renderer, right? I guess what I really mean is, yeah, I said renderer. But what I really mean is it's a tour of the camera, right? I'll use those two terms kind of interchangeably here, let's say. So like I was saying, we lock the texture and then we get some pointer, right? This raw pixels. And then that will get passed all the way through. You'll see that repeat as we go through the wall, drawing walls, that will as you go through drawing walls, that will repeat over and over again. And then when we, in future videos, when we're looking at different stuff, it gets rendered in the camera, you'll see that repeating everywhere else too. Okay, so what do we draw in the camera? We draw a skybox. That is like, switch back to the game. You see all this up here, you know, the stars and whatever that stuff is. That's the skybox. So that's what this does. And we have timers around these, right? So I can keep track in that little widget in the top left that says how long different stuff took. Interesting. I don't know why I think this function doesn't even exist anymore. Is that true? Yeah, so this comment is definitely defunct. I think like that. Do some programming in the meantime. So draw walls. This is the one we're going to deep dive on soon. Then draw floor and ceiling. This is called draw viz planes here. In a future video, when I talk about this, I'll explain it. If you've looked at the Doom source, if you're like familiar with Doom, then you'll know what this. You have an idea of what viz plane might be. This is kind of modeled after the same idea. So we do that. Oh, the order of these actually matters, by the way, but we'll talk about that another time. Oh, no, we'll talk about that just after I finish showing all. So I'll show all of them, then I'll talk about why the order is important. So we've done walls, we've done sky first, sorry, then we've done walls, then we've done viz planes. Then we do mid walls. This is another one as well that is, I don't know if that's, I think in Doom they say mid text, but it's similar idea to mid text. Is maybe it's much further away from the conceptual thing of mid texts than viz planes. Here is the viz planes in Doom, but I couldn't think of a better name for this. These used to be called thin walls, and I think in a bunch of parts of the code it's still called thin walls. Mid walls, thin walls, I'll use those terms interchangeably, I think. So if you hear me saying mid wall or thin wall, I mean the same thing. It's maybe like a synthesis of thin walls from the Wolf 3D style renderer and mid textures in Doom style renderer, like something like that. I don't know if in Wolf 3D if they even say thin wall. I forget what they call them in Wolf 3D, but that doesn't matter. And then draw actors, right? And that's pretty straightforward, right? The actors are sprites, like I talked about in the previous video. So for each one, we're just going to draw a scaled sprite depending on how far away they are in vertical strips. We'll talk about in the video. In a future video, we'll go over rendering those scaled sprites. And here, this is a bunch of stuff because they get sorted by distance. And also, do we check if they're visible? Maybe somewhere else we do, but we just check if we sort them by how far away they are from the player. And then draw traces. This maybe this should probably be put in its own function for now. Actually, in here, do we skip if it's a I think probably what we do, yeah. I think probably what happens is they have sequence none if they're a tracer, so we skip them. But anyway, these are another kind of actor, but like a special kind of actor. So either have this flag that says they're a diamond tracer or they're a pipe tracer, and then we will, for some reason we calculate stuff in here, which seems like messy, but then we'll call these other functions draw diamond tracer, draw pipe tracer. And this is similar to like draw scaled sprite, except it draws something like a geometric shape that is sort of a screen space effect, let's say, in a solid color. It's not textured. And that's for the blaster weapon. I think the player blaster weapon will draw a diamond tracer and the enemy blaster weapons will draw pipe tracers. I'll show you in the game what that looks like, just to break up me talking over the code so much. I'll show you if I get a Like this, yeah. Whoops. Oh, there's some kind of, that's not meant to happen. So there's some bug, but there you go. That's a diamond tracer. Diamond tracer. Okay. And then player hands. Well, you guys seen that many times, right? That's just like your gun when you're playing shooter. And then, yeah, like I said, this is when we pass it over to STL. We say, we've written all the stuff to our frame buffer, right? Now just draw it to the entire screen. And then if you're thinking about like when we step one step up in the chain here, and then we draw UI stuff, that will be drawn on top of this, right? So we'll draw the whole camera, and then all the UI will be drawn on top of that. There's no interleaving of those two things, right? You can't have anything in the camera being on top of anything in the UI. Oh, we did skip one thing. Hold on a sec. Just to be thorough. In here, render present. Doesn't this swap the front and the back buffer? Oh, okay. You don't do that. You don't do that in STL? Okay, well, whatever. Whatever it does is right. So don't worry about it. I didn't skip anything then. That's fine. Okay. So now we've done. Oh, and I said I was going to talk about why it's important that we do this in particular order, right? So this I think is pretty intuitive. We draw the sky. We can draw the sky first. There's no risk to that. Everything's going to be on top of the sky. Nothing should get covered up by the sky. So let's just get that out of the way, and it'll draw to the entire screen basically, right? This is arguably not efficient, but it doesn't take very long, so that's fine. Then we do draw walls. And the name here maybe is a little bit deceptive. We'll go into what that means later on. It's good for this to happen first because it calculates the data that we need to draw these ones, like draw viz planes, draw mid walls. The data to draw those is actually calculated in draw walls. So that has to happen first for that reason. And also draw wall should happen before we draw the actors and stuff, right? Like draw scaled sprite happen before this and before the player hands, because the walls should be behind that. Like you should be able to draw actors on top of the walls. If we drew actors before the walls, then we would end up with actors who are closer than the wall to us, but they're obscured by a wall, so that doesn't work. And the reason it's okay to do actors after this other stuff is because actors are drawn using the Z buffer, which we'll talk about later. But they're sort of special in the sense that they won't draw on top of stuff that is closer to the camera than them. But these other things don't have respect, or I need to double check actually. But let's say for the sake of argument, these other things don't respect the Z buffer, so it's okay to draw stuff that respects the Z buffer after them, but not before them, right? Okay. And so yeah, we draw the walls. We have to draw viz planes and mid walls after we draw the walls because we calculate the data for them in there. And I think we have to draw mid walls after we draw viz planes because mid walls can be transparent, right? Viz planes can also be transparent, but because of the constraints on geometry in the engine, and you can just believe me on this, I could draw a diagram to show you, but for now you can just believe me. We should never get into a situation where a transparent viz plane where you can see a mid wall behind it. And in fact, maybe we never use transparency in viz planes anymore at all now that we have variable height ceilings and floors. That might be a necessary thing in order to not end up with like broken geometry. There may be some situations. Actually, there'll be still some situations where we do that. But that's kind of getting into the territory of like stuff that's not right in the engine by design, right? It's constraints of this kind of simple engine, and the level designers will have to work around it to just not expose these weird cases that don't look right. That's kind of the job. I mean, that's always the case, right? even if you're in a really modern engine, you're not trying to do a physical simulation. It's always smoke and mirrors, and so it's always a dance between the engine and the level designers to not show stuff to the player that looks bad. And there's always going to be stuff that you could do that will look bad that is not worth changing the engine over, right? I think that's kind of part of being a mature designer, is recognizing that. And what else is in order here? We draw traces after we draw actors. I don't remember if there's a good reason. I think just one has to happen before the other logically, so that's fine. Doesn't matter why. And then player hands we draw last, because I think, as I said in the previous video, nothing can ever be closer to you than the player hands. So why not just draw them last? They have to be on top of everything there. It's distance 0. They don't need to care about the Z buffer, right? And then we're done, right? Okay, so that's the end of the tour of the renderer in that sense. Now we're going to do a deep dive on the drawing walls, right? Now, drawing walls used to be much simpler than it is now. I sort of feel like I should apologize. In some sense, I would like to be showing you the older, simpler version of draw walls. It used to be the case that draw walls would come in and it would draw a strip of pixels that was scaled, and that was it. It was like, the function was like that long, right? But now it's more complicated because we have these variable height floors and ceilings, and I'll show you what that means now to ground the discussion. Oops. Put this away because it's buggy. Okay, so if we come over here and have a look, well, if you see like this here, like see what I'm trying to circle with the reticule here, right? That is wall, right? That is wall. It's a wall, it is wall. That is what we would call, in this case, a lower wall. That's the lower part of a wall. And there could be a higher thing up here, but there's not actually. So maybe that's not a great example. Let me find something that's like a threshold that has an upper and a lower part. Actually, there is here. If you look at these windows, right? This tile here. So hold on a sec. This guy here, right? This is a tile, right? It goes infinitely tall. Well, yeah, it's sort of logically it's infinitely tall, right? And it includes everything that's vertically above this square that I'm pointing to. And the lower part of that wall is this gray texture, right? This gray concrete or metal or something texture. And the upper part is bricks. Actually, I can't point my... There we go, I can point it there. So the upper part is these bricks, and the lower part is this concrete. And then in between, there's actually a mid-wall or a mid-text, like I was talking about. This glass type thing, right, is in between. So because we have the variable heights, floors, and ceilings, the rendering of this got more complicated. And you see this part here, like this line I'm showing here, that would, for the tile, is what we would call the floor. And this part here is what we would call the ceiling, okay? Now, right? But stay with me. We're also drawing, I want to point at my screen, but of course you won't see what I'm pointing at. This part here, right, is a viz plane, right? This flat horizontal bit here that we've rendered is a viz plane. And there would be a viz plane here as well. And in fact, I'll just... Oops. Yeah. All right. Yes. Oh, go away. All right. This is a viz plane as well, like this gray stuff down here. You see viz plane up there. Oh, is that a graphical bug? Or... No, that's just you can't see contrast between the two. Oh, come on, leave me alone. I'm doing stuff. Okay. Right. This here is a viz plane. This up. Oh, I've got no clip on still down. Oh, that's fine. Leave it on for now. Okay. This here is a viz plane. This down here is a viz plane. Like I say, now you can see this from the opposite side. This is the upper wall, right? And actually the lower wall now you can't see here because the lower wall is obscured by like the floor from other tiles, right? If we go back out now, you see from the other side now the lower wall and the mid wall and the etc. Right? Okay, so put no clip back on so I don't accidentally screw up the camera again. Okay, so that is what that's what I'm talking about with the lower wall and the upper wall, right? So now we've got to draw the lower wall, the upper wall. When the game was completely flat and we didn't have variable height, floors, and ceilings, there was only wall, no lower wall and upper wall, right? So that was really simple. Now it's a little bit more complicated. We'll go in there now and I'll show you. So, and actually, do I have a drawing? Do I have a drawing ready to go here of this stuff? Maybe not. I don't know where that would have gone to. Shoot, that would have been great. Let me just do a new drawing here on a piece of paper and see if it shows up on the camera. So like, actually, use a pen. It'll show up better. Like if we come in. Okay, so does this show? Can you see this? Yeah, whoops. Okay, so if you imagine we're just talking about like one single tile, right? And oh, my desk is such a mess. Okay, so oops, here. We're talking about one single tile. That's kind of like what I was trying to show you in the actual game engine, right? We've got the lower and the upper part. And so, like I was saying, like this here is like ceiling. This here is floor. And then we've got we'll call this roof. And we'll call this bedrock. I think this is what I call it in the code. So we've got a few different heights here, right? That the engine should cut. Whoopsie, you can't see that now. There we go. So here we'll have the ceiling, what we'll call the ceiling. Sorry, no, the roof height. Here we'll have what we call the ceiling height. Here we'll have what we call the floor height, and here we'll have what we call the bedrock height in the engine, right? In the camera when we're drawing it. Now we need to calculate these for every single wall, every single segment of a wall that we're going to draw, and we'll get into that in a sec. So some of the complexity of this as a result of the ceiling and floor height is having to keep track of all those things. But then also, I told a little bit of a lie, right? I said that this is the roof, this is ceiling, this is floor, this is bedrock. It's actually when we're drawing like one vertical strip for one tile, it's not only one of each of those. It's actually two, right? Because you see here, whoopsie, the bottom part of this, right? That's the back of the tile. There's the front of the tile and the back of the tile, right? There's also on the other side, back, whoops, ceiling, oops. And then, well, you can't see these, right? But there's also somewhere back there, there's back, roof, back, wall, and somewhere there's a back. Now the back bedrock and back roof, I think, are just sort of conceptual heights. I don't think that we need them for the purpose of rendering anything. But oops, so you can see now there's actually some extra. Am I on the wrong side? There's actually some extra heights here that we need to care about, right? And these kind of ones behind. When you're thinking about like we got to calculate something about the geometry or where to draw these columns of pixels, those things matter as well. So yeah, so for actually, this is a concrete example, right? if we want to know how, because we need to know how tall these different columns of pixels are. So at the end of the day, what we care about is like where this starts and how tall it is, right? To draw the front of it. And to draw the viz plane, we need to know this one. So that's common information with drawing the wall. But we also need to know how tall it is this way, right? And to know that, we need to know where the back of it is, right? This guy all the way here, back ceiling. Okay. And back floor. For the floor, we need to work out that, right? That stuff on it. So that's why when you look at the code here, it looks so complicated. We have so many things to worry about. Actually, some of these are even redundant, like fog colors not going to get used anymore. Global fog strength, fog level. Does this get used? Fog distance rate? I think none of these get used anymore. So this can all just get deleted. And that's even stuff from the map format that we can delete. So I get rid of a little bit of that gross stuff for you. And yeah, you can see here like num viz planes, num walls. We set this to 0 at the start of walls. Like I was saying, walls calculates that stuff, right? So those things are deferred. The rendering of, well, not yet. The rendering, the rastering, I don't know, whatever you want to call it, of those is deferred until afterwards. So we set it to 0 here, which is the same as us like deleting the ones from the previous frame, right? And let's see. Okay, yeah. So this is, and then, okay, so now we're going to get into the raycasting a little bit. So like I said, this is software rendering, and it's a raycaster, right? So what does that mean? 640 pixels wide the window is, right? And the camera is. I talked about at the beginning of the video. We're going to send out 640 rays in the direction that the player is facing, and there could be a whole video on that as well. But for now, let's just say we know which way the player is facing, and we use that to work out like this camera plane. No, this camera plane scale. No, not that. Oh, okay, camera plane's been worked out somewhere else. Okay, don't worry about that then. So camera plane, for some reason, we calculated it somewhere else. Maybe that's because it's faster, or I don't know. Maybe I had some idea. I want to calculate it somewhere else for some reason. We have this camera plane, right? And this is not like an airplane, like when you're going on vacation, unfortunately. But it's like a boring kind of plane, like a the world that we're in is sort of not a, it's a kind of halfway between 2D and 3D, right? But we're imagining that it's like a 3D world, and this is a plane cutting through that world that's representing the, what do you call it? Like maybe represents the small end of a frustrum. I don't know what it's called. If anybody knows what that's called, like the narrow part of a frustrum, if you know what that's called, you can tell me. But you can imagine why that's called a camera plane, basically, right? If we represent if we had a camera that was like, oh, did I screw that up? Let's just go with it. If you had a camera that was, whoopsie, that was like that, then this part here, I think, is what we're talking about when we say camera plane, right? In the code. It might be slight. I might be lying to you a little bit, but it's close enough. But actually, this is in 2D, right? So really, the real situation is actually that we have a flat world. We have a flat grid world, and actually the camera plane is just so we have a flat world. The player is somewhere like this, and they're facing some direction, so the camera plane is really just like an infinitely long line going in some direction, right? And the player actually is looking out in this direction. Right. The player is looking that way, and the plane is just orthogonal to that, right? Perpendicular to that. There you go. That's a better way to describe it. Forget about the fake 3D world. So we've got let's see. Yeah, we've got this plane that represents the camera. So now we know we want to look at the stuff that's in front of that. And we just send rays out that would be we send rays out from where the player is based on that camera plane. Let's see. Oh yeah, actually this is right here in the code. You can see, right? That's what I was pointing to. Ray is equal to player look direction, and then we the camera plane is perpendicular to it, right? And actually the camera plane, I guess, is not really going in both directions, right? The camera plane is going in one direction. I think it goes to the... Does it go to the left or the right? I forget. Whatever. It doesn't matter. All that matters, I guess you would just end up with your view reversed if it was the other way around. But it's perpendicular to the way the direction the player is looking, and then we add on to the look direction the amount that we're going off to the side, right? So when we go, and we're going through a loop, right? We go through, like I said, 640 times, right? This thing highlighted. So you imagine you have the players, how do I describe this? Yeah, so you want to cast rays that go out in all these different directions. Like I drew all these little extra arrows there. All these extra ones, right? So we want to calculate all those different rays, 640 of those, where the center of them, the middle, is the direction the player is looking, right? So maybe there's like 320 of those to the left or clockwise of where the player is looking, and 320 of those counterclockwise of where the player is looking, right? And then there's some kind of funky stuff going on here that we do to project those out in such a way that we counteract the fisheye effect of having a camera where it looks at stuff, you know, from some central point. And this is a natural thing that will occur as a result of, you know, having like a point camera. Like, I think our eyes are basically point cameras, right? Maybe I'm wrong. If you're a doctor and you know that I'm wrong about this, please come in the comments and tell me about why I'm wrong. But I think this is the case, that our eyes are basically point cameras like this, or they behave very, very much like a point camera does in theory. And then something in our brain, I think, will have to do some processing of the information that your eyes collect in order to reverse the fisheye effect. Because when you're looking at stuff in life, you don't see a fisheye camera effect, right? You see things as they really are, or whatever that means, right? Like in a more like flat, or not flat. What do you say? In a more kind of like even perspective, where things being off to the left or the right of you doesn't change the apparent distance of them, right? Okay. So we do that, we calculate, and so the level that I wanted to do this deep dive in was like, just say we have the rays. Don't worry about how, because I'm going to do a different video about raycasting later on, right? So we just say we do have a ray, and it behaves like we said there. It gets shot out. It gives us the distance from that camera plane to the thing that it hit, right? So I drew those lines going out from a point, like it was a point camera, but actually what will happen when we do the raycasting here, because of the way that we calculated the ray in the first place, we're going to end up with this perpendicular distance from that plane. So it shouldn't look like the fisheye effect. Just trust me that we have a ray that's like that. Each time we step through this loop, we're going to have a ray that's the ray that just magically makes everything work. And so we have this ray, we do, this is called ray march level geometry. This is also a function of having variable height, floors, and ceilings. When we do the raycasting video, we'll talk about what ray march means and all this stuff. But for the purpose of talking about drawing the walls, let's just say that it did what so it goes out like just imagine it's going in a straight line through the map. The map is like 2D because it's tiles, right? So in fact, well, I guess the diagram from before kind of shows that, but we'll do it. We'll try to do. Right, so imagine the player is here, and they send a ray out, right, and it's hit the edge of a. It's hit the edge of a tile here, 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 here. And then let's say that when it reaches this one, this is a solid wall. Sorry, I'm just drawing a diagram here and talking through it. Okay. So say we've got this circle is the player, okay, and there's a ray, one ray has been cast out by them and it's hit this wall, and you can see I've put little dots where the ray has struck the edge of tiles along the way, right? Let's see, until it finally hits that wall, right? So you can imagine that the result we get back from this ray march level geometry is that we'll get back one tile which is like empty, right? And it'll say I hit it here, and then the next tile is empty, I hit it here. And actually it'll give the front and the back hits, because like I was talking about in the other diagram, to draw those viz planes, the floors and ceilings correctly, we need to know where we hit the front and where we hit the back, right? So it'll give, I went through this tile, I hit the front of it here, I hit the back of it here, next one I hit the front of it, I hit the back of it, until it gets to that wall. And then for the wall one, it'll say, I think it'll still say I hit the front of it and I hit the back of it, but then it will stop. It won't return more, let's say, right? In reality, that might not be the case because... No, actually it will, yes. Yes, it will. If it's a wall, it'll stop because we don't ever see through walls, right? If it was like a thin wall, maybe, right? If it's a thin wall, then we do go through, maybe. Or no, always. If it's a thin wall, we'll always go through. Anyway, don't worry about that. The point is, if it's a wall, we'll stop. Up to that point, and including the wall, we'll return all these hits, and we'll say what the front and the back is, right? I think that's simple enough. So at this point, we've gone through. We do this once for each pixel. This is a typical way that a Raycaster works. You cast out one ray for each pixel each horizontal pixel, each pixel of width in the output, right? And then based on what that thing sent, it gave us back. Like I hit this tile, I hit this tile, I hit this tile. Now we're going to draw a column of pixels, right? So it makes sense. We get back 640. We do 640 raycasts, right? For each one of the 640 raycasts, we will draw a column of pixels that draws the level geometry. And then by the end of that, we've got the whole screen filled up with level geometry, right? Because we've done 640 columns, and each column draws the whole height of the screen, maybe, if there's stuff to draw onto it, right? And so that's what we're looking at here. So we've got, this is the outer loop, this is once for each ray, this is the inner loop, this is for each hit in the ray. So for each one of these tiles, I said here in this little diagram, oopsie, we hit multiple tiles on the way to hitting that wall, right? So for each one of those on the way, we're going to step through this. This is, each hit is one of those, right? Okay. And there's, like I was saying, there's a bunch of calculations here to get the heights of different stuff. So this block of code is like, oopsie, it's like this stuff, right? Looking at trying to figure out how high different stuff is for this one tile to draw it, because each hit that the Raycaster, for one ray, each hit is one tile, right? We do it one tile at a time. Okay. And we're gonna work out what is the distance. So we front perp dist. What is the distance from the camera plane to the front hit on that tile? Is this, and then we use that to work out how high in the camera, so how tall in pixels in screen space is a wall, one world unit of wall, not how high is this wall in total, but, and so this is confusingly named, but it's how high is one world unit of wall at that distance. And for very inquisitive people listening, maybe you'll say, hold on a second, Nelson, that doesn't make sense. The perpendicular distance is 2D. One unit of wall at a perpendicular distance is still, like, depends on how far away it is from the camera in the z-axis. If we're going to say that up and down is z in this coordinate system, right? Well, no. The height of the walls is not perspective correct, right? The height of the walls is that true? Yeah, I'm pretty sure. The height of the walls is like orthographic. So we do have this skewing. Actually, I guess that's what they call, what do they call that? Like Z shear or something in these engines, right? That's why, like, when you're playing Blood, the old Blood, not like the new Kex engine one, and you look up and down, the world seems warped. And in my game, it does too, right? Because the height of the walls, when you look up, let's say if you looked up at a really tall tower in my game, there's no vanishing point vertically, right? It would get like narrower and narrower and narrower, but like the height of it doesn't converge on the vanishing point, right? Okay. So yeah, this is all that stuff. Just imagine that from this block, because this is pretty grotty. Just imagine from this block that we've worked out those things on the diagram, right? Like where things should start and stop. Actually, this is the calculation of where things should start and stop on the screen, because we have to clamp it. Now here we get into a little bit of a trick that I use here. I think it's simple enough to show it on the diagram. If we look at the diagram here, right? Let's see. If you think about the next tile, so say this one here, we're thinking about, this is the hit 1, right? Now hit 2 can only draw stuff inside of here in this little gap. See this little gap in between those two. The next hit from the ray can only draw stuff in there. It can't draw stuff up here or down here, right? Because that's already covered up by a tile that's closer. So what we can do is we have this like draw window start, draw window end here. And we'll write to those. We'll say we've drawn up to here above and we've drawn up to here below already. So then when we go through the loop, we go through the next iteration of the loop, and we see the next hit, we know we can't draw up here and we can't draw down here. We can only draw in this little space in between. So we'll clamp the starting and the ending of these to, with the start and the end. And UW start means upper wall start, and UW end means upper wall end. And why? Because we're drawing columns, right? Why? Because we're drawing columns, the start and the end of the point where we're drawing here is a y value, a screen y value, right? And this is, by the way, the screen coordinates we're using here. 0, 0 is the top left. This is, I think, not. So let me think for a sec. Top left being 0 is obviously how textures work, and we're writing to a texture. So maybe that's the only thing that needs to be said. We're essentially writing to like a bitmap, right? So top left is 0, 0. I was going to go into a thing about DirectX and OpenGL, but it doesn't matter really. Okay. And then let's see, we've got, oh yeah, so light level at, this is to do with the lighting in the game. And it is important for walls, the same as for everything else, but it's pretty boring. This light level at, what it will do is just look at the map. And that's just a number that comes out of the map. So that's set per tile. This light level, oh yeah, this is what I was thinking of. So this is going to do some calculation, but this calculation is pretty boring. All it does is just like take the light level that was encoded in the map and translate it, do a slight translation on that. But it's really one-to-one mapping, pretty much. Oh, actually, we'll use the distance. So the light level does attenuate over distance, so further away things are darker, a little bit subtly darker. And then in here, to actually draw the wall, this is the function that gets called. Draw vertical strip. There's some other stuff here. So if it's a switch, we have some hard-coded logic. If it's a switch, the tile is a switch, you know, like an on-on flicking switch, like a light switch. Then we will try to find the corresponding texture. We have like a thing of like, if it's this texture, then it switches to that, right? And vice versa. And then also, if it's an animated texture, we'll try to find the thing that it animates to, and we'll cover that in a different video in the future. But let's say after this, we've got what the texture is that we want to draw to the wall, right? Then we're going to call draw vertical strip, because like I was saying, we're drawing columns, right? Vertical strip, I'm going to say vertical strip is the same as a column. I'm going to use those interchangeably. And we pass in, like, this is the frame buffer, like I was talking about before. This is the texture we just worked out. And then this is, these two are coordinates, texture coordinates, right? In the texture that we're going to draw. Oh, actually, hold on a sec. These three are texture coordinates, because the X texture coordinate is going to be the same because we're drawing a column of the texture, but and also because we can't, what do you call this? What's this called? Roll, because you can't roll the camera, right? So the X coordinate is always going to be like one thing. We're not cutting a diagonal through the texture. And then top V and bottom V are this is like the texture Y coordinate, or the V. And we need to know the top and the bottom because the strip is going to start at one point and end at another point in texture, right? And this is the light level, like we said. That's going to affect color mapping, which I think is going to be in another video. Is that true? Is color map in another video? Maybe not. Maybe I need to add it. So color map maybe should be in a different video. And this is, let's see, hit front X. Sorry, front hit X is what is this going to be used for? Let me see. Oh, right. So this is pretty interesting. This is a flag, right? This is going to be saying, did we hit the X or the Y? It doesn't really matter. It's just saying, did we hit a north-south or an east-west edge of the face of the tile? And for walls, if we hit one, I forget which is which, it doesn't matter. But if we hit one versus the other, we modify the color. So we make it darker if it's one versus the other in order to do like a fake contrast. And I can show you in the game what that looks like just to demonstrate now. Can you see? Yeah, you could probably make it out, right? So on this is darker than this, right? If you look, this is the same texture, but this is subtly darker than that, which gives this fake contrast. If you look down the middle here, you can see so here you can obviously see that there's a curve here. But if you look here, you can clearly see that there's some demarcation between the two, because on this side it's darker and that side is lighter, right? I guess also there's an angle. What if you look at it like straight on? You can see perfectly, right? This is darker than this, even though these are the same. These are the same. What do you say? Like palette indexes in the texture. It's the same texture and the same bit of the texture, but you can see the difference in color. Anyways, so that's that fake contrast. Oh, I'm so glad that I was actually in the game then. For a second, I thought maybe I was just rambling while I was showing you the code. Okay, so that's what this gets used for, to do that darkening, right? And this comes from the raycasting. The raycast function returns that information. It knows whether it hit east-west or north-south when it hits the tile. This X and so this X is the screen X, right? So we're talking up here. We had the texture X and Y, or the texture UV. Here we've got the screen UV. So this is saying on the screen, this is at pixel X, and the top of the column is UW start, and the bottom is UW end. And then this is saying the distance. And the reason we need that in this function, we'll go in the function now and show the code. The reason we have that here is so that we can fill the Z buffer, I think. Yeah, this just gets used here in the Z buffer. Okay, and now this is like, you know, this is really seeing me in my underpants, seeing me in my jocks kind of thing. It's kind of maybe embarrassing, I don't know. So you can see, oh, do we actually use this here? So this doesn't get used anymore. Neither of these get used anymore. Actually, we can delete these. This bright shift bright mask was for true color, which we don't use that anymore. So that's fine. Okay, so the idea of this function is now we know a lot of information. We've calculated a lot of information up to this point. We know what texture we're going to draw. We know the X coordinate in the texture that we're going to draw, which we call U. We know the start and the end Y coordinate in the texture we're going to draw, which we're going to call V. For these here. We know what light level the tile is, right? We know whether or not we're doing fake contrast darkening on this tile. We know the X coordinate on the screen we're going to draw this strip to. And we know the start and end Y coordinate we're going to draw it at, right, on the screen. And we also know how far away this column of pixels is from the camera, or the depth that this is at, use another way to say it, which is this screen Z, right? Okay, so now this initial rigmarole is kind of boring. This actually looks up so this is actually looking up the texture data for the texture, because up to this point when we're talking about texture, this is just, is it going to show me? This is just enum, right? So, but now this actually is going to look up the data in the game data that we've loaded. Light offset? Do we use this? We don't use this. Oh wait, no, we do use this, don't we? Oh, we don't use it. Okay, you can see that there's something here I've left in that's actually meant to have been refactored or something, because I've left the word foo, right? So that's no good. That should get fixed up, but it functions right. You saw when I ran the game. Okay. So but that other thing could get deleted. So we're gonna say X is equal to screen X. I don't know why we rename that. Maybe there's some important reason. Let's not go through line by line. Let's just like pick out what's important. So we will convert the we're going to convert the texture U coordinate, which is, you know, that kind of, what is the normalized? We're going to convert the normalized texture coordinate. U and V are normalized ones, right? We're going to convert the normalized texture coordinate to like a real texture coordinate, right? By multiplying it by the width of the texture. Then we're going to do a bunch of stuff to do fixed point arithmetic on the Y coordinate in the texture. So let's see, what do we do? This here is going to convert the normalized starting point of the Y texture coordinates to a real texture coordinate in the actual texture, right? Like the same as we did up here. Now, why do we do it on the fractional part? It's because Oh, it's because the wall might be taller than a one world unit or something, right? We know the X is going to be between 0 and 1. The Y might be like 11.5 or something, right? Maybe the start. No, the start might be, depends on it's in upper or lower wall, right? We take the fractional part because if it is 11.5 or something, then we just want 0.5. We don't want the 11 in there. That's not useful for this purpose. And then we will divide this by Texel scale. That name is maybe unfortunate. I don't know why I called it this. I guess because I was just really zoomed in on my thinking when I was doing this fixed point arithmetic. I wasn't thinking about the broader context. But this stuff is just to move from, so this will be like a number between, what's this, the texture is like 64 pixels, right, if it's a geometry texture. So the texture is going to be 64 pixels wide. This will be a number between 0 and 63, but we don't want a number between 0 and 63 here, or we do want a number between 0 and 63, but we want it to be in this fixed point world. Fixed point world. I don't know how to expect. Oh, I don't know what is the correct term for this, but we want it to be in the top. How many? Top 8? 7? We want it to be in the top 7. See, this seems wrong. This comment seems wrong. I think we want it to be in the top 8 bits of the we want it to be in the top 8 bits of this no, here, this in64. We want it to be in the top 8 bits of this in64, right? Why is this int64 and not uint64? Do we really want to have negatives in here? It doesn't matter. Don't worry about that for now. Okay, we want it to be in the top 8 bits of this 64 of the 64 bits. So we're going to divide it by this precision thing. It's reciprocal of 1 left shifted by however many bits. So you can imagine that. Draw a diagram of that. I don't know how to explain exactly. It's hard for me to explain the fixed point arithmetic. But the bottom 56 bits. Yeah, the bottom 56 bits of this are going to be precision, so they're going to be like just fractional part, not whole part, and the top 8 bits are going to be the whole part of the number, right? That's a good way to explain it. So that's what this stuff does here. So we take the starting point of the starting point of what we're going to draw from the texture in the Y direction. And we're going to, so that's between 0 and 63, like I said, because it's 64 by 64 texture. We're going to shove that into the top 8 bits, or the most significant 8 bits of this text Y accumulator. And then, or actually, let's see, this is going to be a floating point number. So then, yeah, so the whole part, yeah, actually, this is more subtle than that. This is actually going to capture more precision than just if we truncated it to an integer. So this is not going to turn out to be a number between 0 and 63, actually. This is going to be, well, it is. It's going to be a number between 0 and 64, but in floating point, right? And then we're going to divide it by this, and we're going to get some number that's between, like, I don't know what, some really, really big floating point number. And then we're going to truncate it to an integer so that we end up with the correct fixed point integer number for this thing, which is very complicated. Yeah, so it's beyond my abilities to explain. I apologize. And then this strip height I can explain. That's really easy. It's the difference between the start and the end in the Y coordinate. That's easy. Sample height similarly is the distance between where we start and end in normalized texture coordinates. And then we just divide one by the other and multiply it by the size of the texture. And this here will give us like how much we should step through the texture in pixels every step. as like a floating point number, right? And then we divide that again, same as we did here, right? We divide that by pixel scale and then truncate it, and then now we'll have an int64, which is a fixed point representation of that floating point number, of how much we want to step each time. And then the stuff with the light level, I mean, this don't worry about that. That's just like, I think this is the maximum light level is 32 or 31. The maximum light level would be 0 to 31. Yeah, maximum light level should be 31. Yeah. So, and this is maximum here actually means like darkest. So the darkest light level we can have is 31. And so we say if it's meant to be half bright, this is, but by the way, the name half bright is a legacy thing. That's a holdover from when this was true color, and I would actually halve the RGB values. But then if it, yeah, anyway, so if it's that, then we add 2 on it to make it darker. But obviously, if we don't go above 31, so that's why we have this check here. And then this foo is just going to get used here when we map this combining. No, it's not combining anything, right? Yeah, this is just actually the. No, this is combining. Yes, sorry. So this light level we got passed in was based on the distance and the light level of the tile. This is adding on the half bright thing, and then we pass that in here when we map the color. Okay, all of that out of the way now. Now we're onto the fun stuff. So now we step through the column, right, pixel by pixel. So we start Y start, Y to Y end, right? And oh, we don't need this I anymore. We can delete that too. That's fun. That makes it a bit simpler. Okay. Yeah, I was wondering why that was still in there. And then now the text Y, so this is the real Y coordinate in the real texture. Actually a number between 0 and 63. That's an integer number, I promise. Now it's really easy to get that. All we do is rewrite shift by texel position, right? So as I said, the whole part of that position in the texture is going to be crammed into the top 8 bits of the accumulator, right? So we just right shift. That's what this operator is here, like the barrel shift operator. We just right shift by 56, and then now we've just got those 8 bits that give us the position in the texture. Why do we need 8 bits for a number between 0 and 63? That's a discussion for another time. I mean, partly it's because this can overflow here, but let's talk about that another time. Color index is just, we look up in the texture what is the color here, but it's palletized color, right? So this actually gives us an index into 256 color palette, number between 0 and 255. If it's equal to 255, that means that this pixel is transparent, right? There is a color in the palette for 255, and it's kind of a funny magenta color, although I don't have my editor open at the moment, but it's kind of a funny magenta color. But you'll never see that color in the game because it's transparent. So if it's that, then we skip, but we still, in that case, we still add on to the texture accumulator. That's important. Otherwise, you'll end up with weird problems whenever you try to draw a transparent texture. Now now it is a true color, right? So this UN32 text color is a true color. This is not a palette thing, right? And we get it by calling this function map color. And map color is going to go look up the palettes in the game. You tell it a particular palette. We'll talk about this another time. This is a palette. The reason we pass this in is because we have palette shifting for stuff like making the screen red when you get shot. And I won't show that just yet because I don't want to distract anymore. I feel like there's so many digressions. We pass, and then so for a palette, let me show what a palette is. It's just an array of a palette is just an array of true colors, UN32s, right? So what is the index into the palette? Well, it is from the color map we need to look up, and this light level is the light level that we passed in, blah, blah, blah. What is a color map, right? So a color map is an array of uint 8s, right? So number between 0 and 255. This is which is familiar, right? Because our palette is 256 colors, right? Okay. So the color map contains indices into the palette. And so for this color that we've passed in, this color map thing is just shifting it to potentially a darker color, right? If this light level is 0, then the result of doing this is just going to be the color itself, right? You can trust me on that. And then in the palette, it's just going to look up the color. The palette contains the colors that, oh, how do I explain this? The palette contains all the colors. If light level is equal to 0, this color map thing just does nothing, and it just returns the color at position in the palette at position color, right? If light level is some higher number, this is going to like translate our color into a darker hue of the same color, which exists on the same palette. But then now the index into this palette here, the stuff I highlighted, will be a different index, which holds the color that's the darker version, right? And actually, I think it's necessary. Well, no. We'll talk about color map another time. Sorry, I'm getting ahead of myself. That's not relevant for this, right? We'll have a video where we talk about color map separately because there's way too much stuff to muddy the waters. Okay, so basically this has just got us the color, the correct color to use from the texture that we're drawing, the wall texture that we're drawing. Now it's really simple. We just, in the frame buffer, what I'm calling frame buffer, we just write that color. It's a true color, like a 32-bit integer. We draw that, and then in the Z buffer, we set the depth that I said up here. We passed in this depth to say how far away the wall is. We set it in here. Now, later on, when we're drawing sprites, for instance, we'll know that if the distance of the sprite is further than this at a particular X and Y coordinate, then don't draw that pixel of the sprite because it's already covered up by a wall. It shouldn't be visible. And then we've drawn, so all of this work, we've drawn one single pixel of a wall, right? Now what we need to do is increment the texture Y accumulator, right? This fixed point texture Y accumulator. And that is fairly straightforward because we've worked out what the step is. So all it is add a step on, but also we need to do mods so that if we've wrapped around the end of the texture, we go back to the start of it again, right? So that's why we do, well, did I say mod? This is not the mod operator, right? There's no mod operator. This is a remainder operator, but we'll for this purpose, we pretend that it's mod because we know that the number is positive, etc., right? That's fine. With text width left shifted by k texel precision. What does that mean? Well, text width is just the biggest thing it could be. Well, sorry, not the biggest thing it could be. It's the what do you say? It's sort of the not rank. What do you call this? I don't know. This is the limit, right? You can't go to text, you can't go to pixel 64. So if this weren't fixed point, we would just say remainder text width, or whatever you want to call this operator, text width. But because we're doing fixed point, we need to left shift it by that 56, right? So that's what we do. That's how we wrap it like that. Maybe I should have just said mod to make it clearer, but we're not dealing with negative numbers, right? So it's the same thing. And then we're ready to go to the next pixel. So each time we step through this, we're going to be adding this step, right, into this accumulator, and then we're going to be right shifting, essentially truncating where we're up to into the accumulator to get the pixel from the texture that we're sampling. That's how we do the texture mapping here. That's what this is, right? This is texture mapping. I didn't say that before. This is texture mapping a column of pixels from the texture, right? And the reason we use the fixed point arithmetic, there's a couple of reasons. One of them is that it is definitely more efficient to just be adding integers together each step than it is to be like multiplying and dividing floating points. Or yeah, so it's more efficient than, you know, doing whatever, like multiplying by the amount of the texture that we're into as a floating point and then multiplying, changing that to a integer so that we can map it on blah blah blah, doing that in the CPU. The GPU does this a different way. Like if you're writing a shader that's going to map a texture, obviously it doesn't work the same way as this, and you'll do it differently. And in that case, you actually have interpolation between between vertices, right? That's a different thing. But yeah, here, so here we're doing in the CPU. So one reason is it's more efficient, and the other reason is that you run into issues of numerical instability if you do this with, well, it doesn't matter if you do fixed point or floating point. Either way, you're going to end up with, if you're adding a step on each time, right? This step is calculated as some kind of like, there's some inaccuracy baked into this step that we've calculated, right? But if you do floating point arithmetic, then there is less consistency in the inaccuracy of the step, right? The inaccuracy of the step is dependent on the scale of these numbers. And when the, you know, as the texture coordinates get further or closer to zero, further from zero or closer to zero, then you're going to end up with a different amount of inaccuracy in this step, right? So with fixed point, we make it just consistent across the board. For every pixel in the texture is going to equally share in the inaccuracy of the step. That's one thing, which I think it looks better, right, on the screen if the inaccuracy is consistent. And also, because we know that the maximum texture coordinate is 63, we can use more of the 64 bits for precision, so we actually have more precision than if it was a floating point, right? If it were a real float, we wouldn't be getting, I think we wouldn't be getting 56 bits of precision for a 64-bit. Like, what is it doesn't matter. Whatever the type is in C++ for 64-bit floating point, I don't think we'd be getting 56 bits of precision, right? So we get more precision this way, and also the precision is consistently applied across all the pixels in the texture and not clustering on particular ones and causing funky as many funky visual artifacts. Okay, so then I think we've gone through the whole thing. That's everything to know about. Oh wait, wait, is there more about drawing a wall? Let me go back to draw a wall. Oh, there's other stuff in draw walls, right? So that's just, I only showed you that's how we draw the upper part. There's also how we draw the lower part, but how we draw the lower part is really the same thing. It's just we use some different bits of this, right? So, whoopsie. When we draw the upper wall, we're using these numbers, and when we draw the lower wall, we're using these numbers here, right? Okay. Same thing, and different texture, right? Because in the representation of a tile in the map, we have a different texture for the upper part and the lower part, and you would have seen that in the game. Here, like I was showing, like, see, this is the lower part of a wall, it uses one texture. This is the upper part of a wall, it uses another texture, right? Yep. That's interesting. There's also, yeah, so that's upper wall, lower wall. So that's actually the drawing of the wall. Then there is some stuff about mids. So if there is a mid hit, there's not always. I showed you one case where there was that window. That's a mid, right? But most of the time, there won't be any mid. But if there is a mid, then we do this stuff. This is similar to what I was talking about, calculating all those distances. So if there's a mid, then, and I guess I need to draw a different diagram to show you this off. Oops, I need a blank area of page. So if there is a mid, then we will have, let's say, like this. Wait, well, actually, my diagram is not a very consistent size here. I don't know. Something like this. Whoops. So if there's a mid, that kind of dark thing in the middle is the mid, right? So now we've got kind of 3/4 view, but the top and the bottom, I didn't make them the same size, so it's kind of scuffed. But this thing in the middle is the mid, right? Like it could be a door or a window or something. This is calculating the tops and the bottoms of those bits. And then we record here, we go add mid wall, and this will go in and I think does it merge them together? Yeah. So similar to Viz planes, it'll merge them together. It'll try to find a mid that already exists that's the part of the same mid, and then it'll add onto that, piggyback on that one. Otherwise, it'll create a new one. That's to draw later. This is deferred. And then similar for Vizplane. Vizplane is like the floors and the ceilings. Here, oops. This is a Vizplane. This is a Vizplane, right? They can get merged together if you have like, and is normally the case, you have like a bunch of floors or a bunch of ceilings that are all the same texture at the same height. Those will actually get merged into a single Vizplane to draw. And so this is like we've discovered one here. We're saying like, what is it? Oh, is this? It has ceiling and oh, so this is just the ceiling. Okay, so we'd actually do the ceiling and the floor of these planes separately. Yeah, that makes sense. So this one is for ceiling. This one is for floor. We calculate same like I was talking about in the diagram. Calculate these like heights, right? And so this for adding a ceiling. We go or a floor. We go in here. We go and look, is there already a viz plane that's been created that's the same texture and the same height? In a video about the viz planes, we'll go through and look at this in depth, right? Because this is kind of complicated logic, but we'll see, can we extend a viz plane that already exists? If we can't extend a viz plane that already exists, create a new viz plane, and then other stuff will add on to us in the future. And then that is, oh, and then also there's a little bit of a, like an early return here, right? So we're talking about, this is still for one single raycast hit, right? So for this raycast hit, if we've already drawn, if we've already drawn all the way down to where there's no more space in between the start and the end of where we can draw into, there's no more pixels to draw to, then just stop, right? And let's see. We'll break out of the loop that is going through hits. So we'll stop looking at more hits from the Raycaster. We don't care about the Ray anymore because there's nothing more to draw. And then we'll go out here and we'll go on to the next Ray, right? So as I said, there's 640 columns, right? Because the window is 640 pixels wide. We do one Ray per pixel. At least in the logic of my Raycaster engine, it's necessary to do one per pixel. If we didn't do one per pixel, then we would just be drawing essentially wide pixels, which doesn't make, what's the point of doing that? We could just scale the image up if we're going to do that, right? So it's very different from how you would render a 3D scene using the GPU, using like like actual 3D geometry, or using geometry that's based on like vertices and primitives based on vertices, right? Like lines between vertices, triangles, particularly triangles made out of vertices, and the triangles can be combined in strips and all kinds of meshes and stuff. It's not like that. And it's also different from other software renderers like Doom software renderer, where the basic primitive of level geometry is like the line depths and the yeah, it's basically like line depths, right? When you see there's a line that's visible, then you draw this geometry, you map textures onto this geometry based on where the line is relative to the camera. I think, and it still does render walls, I think, as vertical strips, but it's not. Anyway, don't worry about it. It's doing. I guess it's kind of doing it more like that my mid walls thing is doing it. Yeah. So this is one way of doing a game 3D game rendering in software is a Raycaster. I think this is a pretty typical Raycaster, except for the thing where the floors and ceilings can have different heights. That's kind of an unusual Raycaster thing, but it's certainly not the first. I'm certainly not the first person to have the idea, and I learned a lot from reading stuff other people wrote about the subject, and also from kind of applying the concepts that were used in Doom as well, right? For some of it. So this video ended up significantly longer than I thought, but I think we covered a lot of good ground. Hopefully that explains a bunch of the conceptual stuff, if not all of the details of the source code, because they're quite complicated and I was covering a lot of ground. Some of these things maybe could be like a whole hour-long video just to get a really rigorous explanation of why everything happens in the code the way it happens, but that's okay. Like that's the point of the videos, is more to give like a conceptual explanation of this stuff, and to also show some of the code, but mostly to explain the concepts in the context of the code. Now, was there anything else? Oh yeah, I guess that's the recap that I wanted to do, right? Was to say that we're doing software rendering on CPU, not on the GPU. It's a Raycaster engine, and that's the way that it renders. We went through and looked at a high level how the game loop of like input, update, output works, right? I showed that in the code. Previous video I mentioned it conceptually, now I showed it in the code, and I showed kind of at a high level the different parts of those steps, the sub steps of each of those steps, maybe you could say. And we looked at a little bit more of game footage and mapped that onto the code. Hopefully this is giving more of a feel of what the actual source code of the game is like, and illustrate a bit more how the rest of the series is going to go. As always, I encourage you, if there's stuff that was interesting that you didn't understand, or you thought I didn't explain it clearly, or it was ambiguous or anything like that, please ask questions in the comments, and I will endeavor to answer those in a follow-up video. Either it'll be, just a normal series video. I'll pick up a question and answer it in that, or it might be a separate video that's just about your question, depending on what the question is like, or it could be, a video that's covering a bunch of questions together, I guess. But either way, what I'm trying to say is I will endeavor to answer those questions, so please ask them, and they're really important for me to know what stuff's interesting for people to do more explanation. And also, I just really enjoy answering questions about it. I love talking about this topic, so don't hold back. And I look forward to seeing you all next time on Programming for Posterity. I'm Nelson. Have a good one, guys, and I will see you later.